we're talking about for a series and for a transform, and using to deduce constant inequality. So what did we learn? So we're interested in a function u from R2 into R2. We're going to write u with its coordinate functions u1, u2, like this. We've learned about taking the Fourier transform. So we're going to write uk Fourier transform of this guy. I don't know, because k was a frequency. Let's call it up. And we have u. Let's actually put in what the frequencies are. Okay. Let's just do this whole expression again. So previously I used k and m, but let's use k1 and k2. And we have minus infinity to infinity. Let's use x1 and x2 this time. And we have e to the minus I minus 2 pi I of x1, x2, the product k1, k2, like this. And then the x1, the x2. This is our Fourier transform. This is now a function from R2 to the complex numbers. Okay? And this thing is our uncountable sequence of coefficients that break down UP, and therefore we can represent UP with a simple inverse Fourier transform like this. Had P, P1, P2, e to the 2 pi I, K1, K2, the product X1, X2, K1, K2. Right, that's where we were. And then once we have this representation, if we differentiate through with respect to, say, the R partial derivative where r is 1 and 2, so belongs to 1, 2. If we differentiate through, so we have up comma r, x1, x2, this stuff, u have p, q1, comma q2, 2 pi I. We're differentiating with respect to the r coordinates, so we're going to pick up a k r here, and then just e to the 2 pi I, k2, x1, x2, k1, k2. So, and since this representation is unique, instead of putting this thing here, this thing, we instead could have the Fourier transform of the partial derivatives of up comma r, Fourier transform of this guy, k1, k2. That would also be true because that's our theorem. That's what Fourier representations tell us, right? Which means that the partial, with its Fourier transform, k1, k2, has this very convenient form that it is just 2 pi I k r of the original guy. So like this. And that is excellent because this is all just recap of what we did before. Let's take the Fourier transform of the entire matrix, which means this is the Fourier transform of each individual coordinate of the matrix, or each individual entry of the matrix. That messed up. together together, K1, K2, and then let's read off what it is. So, first derivative of the first coordinate, so we're going to have, let's just pull out 2 pi I straight away. 2 pi I, so the first derivative of the first coordinate, so we're going to have K1, B1 hat. I'm not going to write K1, B matrix here. The second, so we have K1, 2 hat. Then we're going to have, this is now going to be the second derivative of the first coordinate, so it's K2, 2 hat. And then this is K2, 1 hat, and this is 2 hat. This. Yeah? In other words, this thing becomes very convenient and like this. K1, K2, just becomes a rank 1 matrix. Okay? And that is going to make us very happy in a very short amount of time. Because rank 1 matrices has some convenient algebraic properties for this purpose. So recall what we're trying to do is prove Korn. For L2 functions, which is the following, the double integral of gradient of u squared dx dy is less than a constant of double integral of the projection onto the symmetric matrices, which is the same as the distance away from the skew-symmetric matrices by the orthogonality of the symmetric and skew-symmetric matrices, like this. Okay? This was our goal. And then we are going to be able to do that now that we know that the Fourier transform of a gradient from R2 to R2 is a rank 1 matrix. In fact, it's true from Rn to Rn. All right, a bit of algebra. That's spell out. So let's pick it up. Right. So notice following thing. If we have a rank 1 matrix, let's look at this. Look at this rank 1 matrix. So take out B is A1, B1. So this A thing times the first infinite product. So we're going to be row and column. So we're going to have A1, B2, and then we're going to have A2, B1, and then A2, B2. Right? So if we take the actual norm of this thing in the Hilbert-Smith sense of the norm, which is we're going to square all the entries in square root, then what are we going to get? We're going to get A1, B1 squared, A1, B2 squared, we're going to get A2, B1 squared, and we're going to get A2, B2 squared. Yeah? That's what we're going to get. And we can factor some of this stuff out. Let's factor out the A1 squareds. We're going to have B1 squared plus B2 squared. Let's factor out the A2 squareds. Again, we're going to have A1 plus A2. Sorry. B1 plus B2, so B2 squared. B1 squared plus B2 squared. So overall, this thing is nothing other than this thing. Right? Because we just factor out B1 squared plus B2 squared. Yeah? So the Hilbert-Smith norm squared of the rank 1 matrix is just A squared, B squared. Yeah? Cool. And remember our decomposition into conformal and anti-conformal, right? So if we have matrix A, B, C, D. Sorry. When I said conformal, anti-conformal, I meant symmetric, anti-symmetric. We also have these conformal into anti-conformal, but we don't need this one at this particular moment. So we're decomposing this matrix into symmetric and anti-symmetric. So now to do it, do this. That thing forms a symmetric matrix, and we do this. Like this, yeah? And if we add these two guys together, we get exactly the same thing.
these are nice linear transformations. So this is what we're gonna, this is the thing that defines the projection of symmetric matrices. So we write P sim of this matrix, this matrix A. P sim of the matrix A is this thing, and skew symmetric part is this thing. So it's P writes U. Again, nice linear projections. Everything is very, very nice here. Yeah? Cool. So let's see what happens when we project, when we take the projection of a rank 1 matrix onto the skew symmetric matrices. Let's see what we get. So P of skew of A corresponding B. What is the P coordinate? Is this one. So we're going to have A1, B2, and the C coordinate is this one, which is A2, B1, over 2. Missing out the other entries of the matrix. Let's do them. So it's 0, and then this is the B, which is this one, so it's A1, B2 minus A2, B1 over 2, like this. This is projection, and then it's minus this, so then it's A2, B1 minus A1, B2 over 2, and the other entries is 0. Yep. Cool. And let's take the Hilbert-Smith norm of this thing. So if we take the Hilbert-Smith norm of the skew symmetric matrices of this thing, what are we going to get? It's going to be this thing squared plus this thing squared. Actually, let's just, let's do this thing, not the actual, let's square it. So we're going to get this thing. So I'm going to write this as the inner product of A1, A2 with B2 minus B1. So it's going to be A1, A2, dot product, B2 minus B1, like this, squared over 4. That's that entry squared, and now this entry squared, but it's also got the same form. It's still going to be almost the same form, so it's, okay. Let's write it like this, A1, A2, dot product with minus B2, B1, like this. So it's almost the same, with up to a minus sign is exactly the same. Okay, let's just keep it this way. Squared like this, over 4. Right? What is this? Well, the inner product is less than the norm of this thing squared. I have to know what the inner product of this thing squared is less than this thing squared times this thing squared. So this is less than A squared, B squared over 4 plus the same thing, A squared, B squared over 4. And then all of this stuff is therefore less than A squared, B squared over 2. No? Cool. Everybody happy? No? So, what does that mean? That means that, well, let's try and remember this. So, that means that when we take a rank 1 matrix, okay, whose norm is equal to norm of A times norm of B, then the orthogonal decomposition into the symmetric and skew symmetric part is such that when we take the norm of the skew symmetric part, its norm is less than A mod A times mod B over square root of 2. No? I'm going to raise the board. I want you guys to tell me why that is useful for us. In particular, what does that tell us about controlling the norm of the right-line matrix with the normalistic symmetric part? Okay, tell me about controlling the norm of the right-line matrix in terms of controlling the norm of the symmetric part of it. So we just learned that the absolute value or the norm of the projection of the skew symmetric of A cross product B is less than 1 over root 2 mod A mod B, and the Hilbert-Smith norm of the right-line matrix is just this. Yeah? So, any takers? It's just going to be the triangle inequality, right? So, what do we know? We have this orthogonal decomposition that B is equal to the projection onto the symmetric part, B, plus the projection onto the skew symmetric part. Yes, so we can put absolute value signs around everything. And then this is going to be less than the projection. Triangle inequality, equals product B. Plus this thing. Like this, yeah. And we know that this thing is less than, let's write it over head. This thing is less than, mod A, mod B over square root of 2, like this. Yeah. And therefore we can just put it onto the other side, right? And still have something left. So we're going to have 1 minus 1 over root 2 of mod A equals mod B is the same as mod A equals mod B minus the projection of the skew symmetric matrices like this, which therefore is less than projection of the symmetric matrices of this. Yeah, cool. Which gives us the bound that we want. Everybody with me? Yeah? Thumbs up. If so, thumbs down if you have any questions. All right, super. All right, so the thing that we want is true for constant value gradient functions that are rank 1, right? So this is the inequality that we want, except for gradients when we integrate this vector L2. But we have Planchel's theorem, which is the ultimate generalization. Well, maybe not the ultimate, maybe it's a more general setup of Fourier analysis where this is still a special case. But a far-reaching generalization of Pythagoras' inequality is this thing, that if we take the L2 norm of a function and we take the L2 norm of the Fourier series, then they agree. The Fourier transform, and they agree, like this. This is Plancherel, which I can't spell. And this is just a generalization of what we saw before when we did this for Fourier series. I'm not going to rewrite it, but that's exactly what we wrote for Fourier series when we took our orthogonal basis vectors e to the I, k, x, and we had to divide by the square root of 2 pi, something like this, right? So when we did this and then took the inner product of these coefficients without functions and then squared that thing turned out to be the same as L to norm. So this thing is exactly in the generalization. Now we have this uncountable infinity of coefficients represented by the Fourier transform. Yeah? So this is another true fact, which again follows fairly. I kind of showed you this module of the fact that swapping intervals and sums. This thing formally here doesn't follow too much problem. If you set up the convergences in a sufficiently correct way. All right, so this is what we're going to use, and this is how we're going to argue. We're going to, okay, so we are doing the double integral of the gradient of our function squared, dx1, dx2, yeah. And then this is equal to the double integral of the Fourier transform of the gradient. Squared now the integrating over k1 and k2, which are the frequencies. Right? That's just using Plancherel's theorem, because what this means is the Fourier transform of each one of the coordinates of this matrix. Yeah? It's directly applying this. Yeah? But we know that this thing here is a rank 1 matrix. Right? This is a rank 1 matrix. Yeah? Every k1, k2 is a rank 1 matrix. So then this thing is controlled. We even have a constant here by 1 minus 1 over square root of 2 of I guess we have to square everything, so probably it's a linear expression. Okay, so this projection onto the symmetric matrices of the Fourier transform, like this, squared dk1, dk2, like this. Yeah? Exactly applying this inequality that we established with this. Yeah? So this is our inequality that we're applying here. Everybody okay with this thing? Yeah? Cool. Now, Fourier transforms, as we showed, are linear. These are linear things, right? So if we do the Fourier transform of f1 plus f2, it's the Fourier transform of f1 plus the Fourier transform of f2. Yeah? And same with multiplying by scalar. Just pull it out. Yeah? So what is this thing here? This is a linear combination of these guys. Right? This is a linear combination of the Fourier transforms of the coordinates of the gradient. Yeah? Or the entries of the 2 by 2 matrix, so this is the gradient. Yeah? So we can swap the order of doing this because it's just acting on this linear. Okay? So this thing is the same as doing the projection onto the symmetric matrices of the gradient, okay? And then taking the Fourier transform like this. Okay? Squared. And we're still integrating with respect to k1, k2, because this is still the Fourier transform, we're still integrating in frequency space. Yeah? Cool. But then this thing itself is just a matrix. Right? And we're taking the Hilbert split norm, so it's just all the entries squared, so we can still apply Plancherel theorem, and then this thing is the same as the double integral of projection of the symmetric matrices of the squared. Now we're integrating with respect to x1 and x2 because we're back in the real variable space. Okay, so formally it's really easy, just swapping symbols around. But obviously there's a lot going on encoded by this rather simple line. Yeah? And the real heart of this is the fact that when we take the Fourier transform of a gradient of a function from R2 to R2, it turns into a rank 1 matrix. And rank 1 matrices are very specific algebraic things. And that is the heart of algebra. A lot of stuff, a lot of elliptic regularity comes down to things very similar to this. It's a little taste of how powerful things are when you transfer them into frequency space and try and do your estimates there. All right. So that is the Korn's inequality I claimed, right? Because again, projecting symmetric matrices is the same as the distance away from the symmetric matrices. Because they are Fourier subspaces. And in the actual one that we used, we did this over a finite domain and we subtracted the symmetric matrix here, right? But if you have the integral of this guy away from the symmetric matrices is small, then if you have this over a finite domain, then the average matrix over that finite domain would also be close to the symmetric matrices, right? So you could think of the average of the gradient being interchangeable with the closest symmetric matrix. So what I mean is symmetric matrices is a subspace. If we integrate over and it's close to the symmetric matrix, then the matrix that represents the average of those is pretty close. So then we can just pick the closest symmetric matrix, right? And if we think about this guy as being the u minus the average of the gradient, then it's exactly the form we want, because the average of the gradient will be 0 because it's a function which is L2, so it's vanishing in infinity, right? So we could also write this thing. I mean, it's a vacuous thing to write, but we could write this thing minus the average of the u, like this, squared dx1, dx2, no? Because the average of the gradient is 0, no? But when the average, I mean integrating over all of space, you know? But this guy is the average of the u, and these are skew symmetric matrices, and we know that this thing is small, and we know a small domain or a finite domain, then we can swap the average with the closest skew symmetric matrix and have the same estimate, and that's how this thing starts to look like the version of Korn's inequality we actually used. But to actually argue that, we need something called Plancherel inequality and a few other little bits of technology in the Sobolev spaces, which is what we're going to introduce now. Cool. So we're going to discontinuously jump and start talking about Sobolev spaces. Some of you know a lot about Sobolev spaces. Josh is writing his thesis in exactly this kind of area. How many of you are familiar with Sobolev spaces? So shake your head if you've not seen them before. Actually, give me a thumbs down so that I can see them clearly if you've never seen Sobolev spaces before. 2 of you. Okay. All right. That's not 2. All right. Good. So we're going to. So I'm not. This is again quite an involved subject. Do a whole course on this easily, and we're not going to do that. We're going to I'm going to give you a flavor of what's the important thing about Sobolev space. I'm going to give you a caricature, like a cartoon sketch of the main things you have to care about when you work with Sobolev functions as opposed to C1, C2, C3 functions. Okay, that's my goal. And then for the rest of this time, we'll be working with Sobolev functions, and hopefully they will seem quite natural to you. So here is where it starts. So space. And we're going to start by defining weak derivatives. So we start just for functions from R to R. Let's take u from some interval AB into the real numbers, and suppose u actually does have a derivative, C1. Then take some, we call a test function, some phi, which has got compact support, so it's compactly supported in our interval, a b, and it's as smooth as we like, so we can take this infinity. And then notice the following thing, and if we take the integral of the derivative times phi from a to b, then just by integrating by parts, I'm the same as minus the integral from a to b of u phi prime dx, right? That's easy enough. Yeah? All right, so what you might have noticed when we're doing the stuff showing Mulder's theorem and many, in fact, all the stuff we're doing here, is that we use derivatives all the time, but we don't use them pointwise. I'm never doing things pointwise with derivatives. I'm never looking at Taylor series. I'm never dealing with anything happening specifically at any point. What I'm doing is I'm doing estimates. I'm integrating gradients. I'm integrating the norm of gradients, right? That's what I'm doing all the time. Yeah. So if all you care about is integrating gradients and not pointwise behavior of gradients, the main tool you want is integrating by parts. That's what we use multiple times, right? In the proof of Mulder's theorem, integrating by parts. And this is the statement of integrating by parts. So the idea is as follows. So we have C1, this is true. So suppose we have just a function, let's say W, which is, say, in LP of interval AB, okay? And the following is true, that whenever we integrate this, let me say and there exists some, let's call it W hat belonging to LP of the same interval, such that the same inequality holds true. Whenever we integrate from A to B of W times phi dx, that's the same as integral minus from A to B of W hat. Write that better, so I put W hat of phi dx. This is the key point for all compactly supported test functions in our interval. Suppose we had some function like this. In the case that W happens to be C1, then this W hat would just be the derivative. But it turns out that we have a very successful, very powerful theory, in fact, much more powerful than the theory of simultaneous functions, where we consider functions for which the only notion of derivative is this, that we have an LP function that allows us to integrate by parts. Okay? Yeah? And that is what we call the derivative. Yeah? Then take W prime to be defined to equal to W hat. So the derivative is defined to be this LP function for which this holds true for every single test function. Okay? First thing to point out, this is not unique, right? We can change the derivative of a set of zero measure and this will still be true, right? This will still be true. So it is not unique. We lose uniqueness of derivatives. We can change them on a set of zero measure. And that also means we lose pointwise derivatives because there's no meaning to having a pointwise derivative because the derivative of a Sobolev function, a priori, we'll later learn about something called traces, but at any particular point, as I've defined it here, the derivative doesn't necessarily make sense, right? So we lose pointwise properties. So first we say that we define. So then W is a Sobolev function. Sobolev. And in this case we say W belongs to W1P of the interval AB. And the norm of this thing is just the LP norm of the function and the LP norm of the gradient. Oops, P. Like this. And W prime is not unique. It is not unique. But there's an equivalence class, things that are equal to it almost everywhere are unique. Okay? Just like LP functions are not unique, but they are fundamental equivalence classes. Yeah? So in doing this, we sacrifice the pointwise notion of gradient, which is how I spent years talking about gradients, calculating derivatives, teaching students about this. It's a pointwise concept. And this thing is dropping this. We're dropping this concept, right? But for an enormous payoff, for an absolutely huge payoff, because if we consider, for example, okay, so if we just take something like this, which just like something like this, and then lifts off like this, right? And then we just make this transition sharper and sharper and sharper, so it's less of a smooth curve, more like a corner, until it converges to something which is just literally a corner like this, and then the gradient has a discrete jump, right? The gradient has a jump, we're no longer in CK. But all these guys are nicely C1, just make the corner softer, make the rounding of the corner smaller and smaller, but the limit it's not. You know? So C1 functions, I mean that's not a full example, but it turns out that C1 functions are not a Finite space. And that's really a problem for us because we would like to use the tools of function analysis, we'd like to use tools of calculus variation, we'd like to minimize the function classes, and we can't do this with CK functions because we can take some limit of CK functions and end up some which doesn't have a derivative anymore. But Sobolev functions are a Finite space, and that gives us a whole payoff, the truckload of gifts that come from that, which is enormous. It's like, we'll talk, go into more detail in a second. Many linear problems in PDE solved by ad hoc methods, kind of complicated ways, until this idea, which is rather simple in a way. And then all these things, all these separate methods all became absorbed by just one general idea, which was to solve the PDE in Sobolev space, either using something like Ries's representation theorem or just minimizing some minimization problem, and get what we call a weak solution which holds true when we test against test functions, and then recovering actual pointwise solutions with regularity of PDE. So that's an extraordinary idea. It's like a chess sacrifice. You guys probably play chess a bit. When you're playing chess, you're in a position and you want to get a better position at the cost of losing a piece, and then you sacrifice. So you're down a piece, but your position is greatly improved. This is what this idea is like. You sacrifice information, you sacrifice pointwise derivatives, and that allows you to move much further. And you're in such a strong position, you actually can recover pointwise derivatives for many, many nice PDEs with PDEs. Recover all the old results that done by different ad hoc methods. Okay, let's jump on ahead. Let's do this in higher dimensions. So I suppose we have some function which is defined from Rn. So let's say U goes from Rn into R. Then what would we expect if we try and do this? Well, the way to do this is just by asking yourself what would happen if we tested against smooth test functions and we had an actual pointwise derivative. So if we did this, do I want to do a domain? Okay, so I'm not going to write double integrals because it's an Rn, so we're just integrating over Rn. Maybe let's take a domain. have omega contained within Rn. Okay, so we're integrating over this, and if we have u tested against a test function where we take the partial, let's take the partial kth derivative, like this. And now dx means the n dimensions will dx, dx1, dx2, dx3, dxn. Okay? Then this thing is equal to this thing, comma k phi dx for all test functions, phi compact support inside omega, scalar valued. So unless I put something here, it's assume everything is scalar valued. Unless I just need to realize it's scalar valued. So this is just, again, integrating by parts, right? Feel happy with why this would be true if we have C1? No? Because we just do the kth derivative of the product is like this. And then if we integrate this across the domain where this thing has got 0 on the boundary, right? So if it's another domain like this, and then this is the kth direction, so ek, then we integrate along lines like this expression will be 0 just by fundamental theorem of calculus, yeah? And therefore, the total integral of the entire domain will satisfy this thing if we have an actual similar derivative. Are you all happy with this? Give me a thumbs up if so. We've used this before, but I want to make sure you're happy. Sanka, how do you feel about this? You okay? Okay, cool. So, if we have this holds true, so I'm going to erase this part. If we have this holds true for all test functions for these u comma k, which belong to LP of omega, yeah, then the actual gradient, which as you know is an n that is effectively equal to Rn if we have a classical pointwise derivative, the actual gradient u of x is equal to u comma 1 of x, u comma 2 of x, u comma n of x. And this thing is a vector value function in LP. Okay. So we want all the coordinates to be in LP, so we have that this is true. This thing, the p dx, is less than infinity. Yeah? Cool. And if we have a vector value function, then it's exactly the same. We just consider each one of the coordinates as partial derivatives, so we can have a matrix valued derivative where the matrix is a matrix where each of these entries are in LP. Yeah? Every other, all the kind of algebra of the setup follows exactly the same. The point is we now have gradients which are LP functions that will define almost everywhere, and they satisfy what you would get if you can integrate by parts when you test against some of the test functions. That's the idea. No? And you might be thinking, okay, well that sounds like kind of my watch is dead. How much time do we have? Two minutes. Okay. All right. So that might sound like not much of a, it might sound kind of weird when I first saw this stuff. I thought, what's the point of this? It seems like it doesn't seem like it's worth a lot of things. But I didn't even see why it was particularly different for different p. And that's the main thing I wanted to show you is that these things form different spaces for different p's. And the bigger p you have, the more control you have on the function u. And to do that, I'm going to show you a specific case of the Fourier formula, which is just actually integration in polars, but we've used it already and we're going to need it again, so I'm going to share it with you. So there's a little lemma, and it just follows from multivariable calculus, change of variables. So let's do this quickly. So there's a little lemma, suppose we have some function f from the ball into R. Then we can do this integral over the entire ball. Let's do this in R2, just as everything is simpler. So the integral of the ball, let's do a double integral since we're only doing an R2 of this thing, f of x, absolute value over mod x, since I do a double integral, okay, forget the double integral, let's just do one. This, dx means integral over all of R2. This thing is equal to the integral from 0 to 2 pi, integral from 0 to the guy, that's right, cosine of theta, sine of theta, this of f, that's right, maybe z, dh1 of z. So this is the one-dimensional integral, the path from 0 to this thing, and then the theta like this. Okay? That's what we are going to show you. And you might be familiar with this, you might be happy with this, but in case you're not, I'm going to show it to you because we're going to use it to show how different these guys are from different P. All right, so I want to just get this done so we can start off. Please leave if you have to leave, no obligation to stay. It's just going to be up in video, and maybe you know this anyway, so just go if you have to go. But let's just quickly show this. All right, so why so? Proof. All right, so let's do the following. Let's define P of x1. Let's just put it in terms of x. Let's define P of x to be mod x, and then the argument of x. So like arg of x, which is the same argument, you know, from complex analysis. It's the angle that define that's defining this x, right? So arg of x we can take to be arctan. Arctan using the first quadrant of x2 over x1. Now we do the same thing, right? So x1 and this is x2. Like this. This is a nice transformation. And so this is transforming all of R2. P goes from R2 into 1. So into positive numbers, cross product 0 to pi. Now, let us calculate the determinant of the derivative. So first, let's calculate the derivative. So if we take the kth partial of this thing, then what's it going to be? So it's 1 over 2, x1 squared, x2 squared, minus 1 over 2, and then just 2xk. So it is xk over mod x like this. If we take the first partial of what I call the argument function x, then it's differentiating this thing, so it's 1 over 1 plus x1, x2 over x1. And then we differentiate with respect to this coordinate, so we have minus x2, or with respect to the inner function, I should say, minus x2 x1 squared, just the chain rule, multiply this through, so minus x2 over x1 squared plus x2 squared, and that is just minus x2 over mod x squared. Let's do the other partial. And same kind of game, so we have 1 over 1 plus x2 over x1 squared, and differential respect to x2, so we're just going to have 1 over x1, so we're going to x1's over x1 squared, and that's just x1 over mod x squared, like this. Yeah? So then if we take the whole matrix of this derivative like this, so this one, the first coordinate, we're going to have x1 over mod x1, then in arc with respect to the first derivative, we have minus x2 over mod x squared. Then in the first coordinate with respect to the second, so we have x2 over this, and then second coordinate with respect to the second, x1 over mod x squared. Therefore, determinant of the gradient p of x, no? Is just x1 squared plus x2 squared over mod x to the 3, which is just 1 over mod x, like this. Right? So that gives us Jacobian of this transformation. So, that's a technical kill this one. So, let's just use that. Let's write this thing. So, the integral of the polar x1 of f of x over mod x dx equals integral of b1. And we now know this is the Jacobian of this thing, so let's write this as f. Let's write p to the minus 1 of p of x. P is usually seems to be an invertible thing, right? Times the determinant of gradient like this, dx, right? Cool, but now we're in a position to do change of variables, right? So this is just a multivariable calculus, and this theorem is, this step is, you can just work out the Jacobian, the change of variables formula just by breaking up into little pieces, doing the standard thing on how you prove all these multivariable calculus formulas, breaking little pieces, look at the affine piece, put them all together, you have a Riemann sum passed to the limit. So all that stuff is easy to prove. You guys hopefully have no doubts about this. So then that's the integral of the image of B1 with respect to this transformation. And now with respect to these new variables, so f of p to the minus 1, let's call the variable z. Like this. Where z now is in this space of plus product 0 to pi. Okay. So it's this, like this, dz. And then let's now, so z is inside this space, so we're integrating the real numbers and then just the angle 0 to 2 pi. Let's just do the Fubini and let's note the following, that so if we have z in this space, so p to the minus 1 of z, this z1 coordinate is in this space, which represents the magnitude, and this z2 represents the angle. So this will be z1 of cosine of z2 sine of z2, like this. Yeah? That's what this does map out. So then this thing is this, and what's the image of this thing? This thing is the same as the integral from 0 to 1, cross product 0 to 2 pi, and now we've got f of z1 cosine z2 sine of z2 like this. and dz, and now we can just do integrate. Flipping, let's integrate one bracket after the other. And let's do the integral from 0 to 2 pi on the outside with respect to z2, and let's do the integral with respect to z1 from 0 to 1. And then we have the value of f of, let's write it as z1 times cosine of z2, sine of z2, like this. And this is respect to dz1, and we have dz2 outside here. And that's exactly what we want, because what's that? That is the integral from 0 to 2 pi of just the integral from the center to this point, cosine of theta, cosine of z2. Let's actually call it now theta, let's change variables. Z2 now becomes theta. This, and then we're going to have, let's call this R, that function, just given different labels. Actually, you can just write like this, just directly write like this. I used 10 before, unfortunately. Let's write this. You think one of this. Right, so this thing is a parameterization of this path, so this is just exactly the one-dimensional curve into a one-dimensional curve we know, and then this is the theta, right? Which is what we claim right here. Yeah? All right, so at the cost of having a kernel that blows up in the center, we can integrate out on these rays like this. Yeah? And again, this is just integration in polars done from first principles, and we're going to use this. We're going to use this later on, in lots of times, specifically because we do want to integrate gradients in some way, but we have to get some paths where the estimates hold, and that allows us to do that right here. All right, that's it for today. I will see you all on Monday. Have a great weekend. See you all later.